Hello, Chem 1B. This is chapter 20, lecture video 6, and we're going to be talking about nuclear binding energy. So, nuclear binding energy is defined, as you can see here, the energy required to break a nucleus apart into the individual protons and neutrons that make that nucleus up. Now, as a general statement, the mass of the individual particles within the nucleus usually add up to a larger mass than the nucleus itself. So for instance, if I have a lithium atom, we're going to do a problem with lithium in the next slide, that is lithium-6. That means it has 3 protons and 3 neutrons. If I added up the individual masses of all those protons and neutrons, I would get a larger number than the actual mass of one lithium-6 nuclei. This difference in mass being larger for the particles that make up the nucleus versus the nucleus itself is known as the mass defect. It's been theorized that the missing mass is actually being converted to energy to hold the nucleus together. And using Albert Einstein's equation, we can relate mass to energy, E is equal to mc squared, and we can use the mass defect to calculate the energy being used in the nucleus to hold it together, known as the nuclear binding energy. This equation here is what we're going to be using, and that delta M is the mass defect. It's the difference between the mass of the particles that make up the nucleus and the mass of the nucleus itself. Now, there are a couple things about this equation. This has to be in kilograms, and because C needs to be in meters per second, and we're squaring that, the units of this equation gives out kilojoules times meters squared over seconds squared. And if you didn't know, now you do. 1 joule is equal to 1 kilogram times meters squared over seconds squared. And it's this reason why we need to use kilograms in this equation, because effectively this equation will spit out an answer in joules as long as we use kilograms and the normal units for the speed of light, that is meters per second. Okay, so let's do an example problem of this equation in this problem, in this topic, nuclear binding energy. Calculate the binding energy per nuclei and per nucleon for a lithium-6 atom. The atomic mass of lithium-6 is 6.015125 AMU. AMU stands for atomic mass units, also symbolized just by a lowercase u. The atomic mass of a hydrogen-1 atom is 1.007825 atomic mass units, and the atomic mass of a neutron is 1.008665 AMU. So we need to calculate our nuclear binding energy, which means we're going to be using our equation delta M times C squared, right? This is equal to our E, and E is what we're calculating here. Now, delta M, like I hinted at earlier, is always going to be equal for nuclear binding energy problems. Delta M changes for other problems regarding like fusion and fission calculations. But for a nuclear binding energy problem, it's the mass of the particles minus the mass of the nucleus. God, I can spell nucleus, I swear. So let's look at lithium-6 in this regard. Lithium-6 has 3 protons, because the atomic number of lithium is 3, and 3 neutrons. So, therefore, let's calculate the total mass of the particles here. We know the mass of a neutron is 1.008665 AMU. Now, we're going to change AMU a little bit because it's easier to work with grams per mole, and if you remember from Chem 1A, 1 AMU is equal to 1 gram per mole. So I'm just going to ignore the fact that I was given an AMU and change it to grams per mole. My life is easier if I do this. The next thing we have to figure out is what's the mass of a single proton. Well, if we look at a hydrogen atom, specifically a hydrogen-1 atom, hydrogen-1 is just a single proton by itself. So the mass of a hydrogen-1 atom is the same thing as the mass of a proton. And again, I'm going to convert to grams per mole. Now, if I want the mass of particles, That's going to be equal to 3 times the mass of my protons, because I have 3 protons, plus 3 times the mass of my neutrons, because I have 3 neutrons. And this will give me the total mass of the particles in the lithium nucleus. This gives me 6.04947 grams per mole. Now the next thing I want to do is I want to calculate delta M, right? So if we think about this, right, delta M, our mass defect, is equal to our particles minus the mass of the nucleus. And we were given the mass of the nucleus in the problem. So I have 6.04947 grams per mole here, minus 6.015125 grams per mole. And I can calculate that. So I have this 0.034345 grams per mole. But like I said on the previous slide, we can't use grams in this equation. We have to use kilograms. So the next step is to convert this from grams to kilograms. We hopefully remember that conversion. We're going to get 3.4345 times 10 to the negative 5 kilograms per mole. All right, so now I can plug this into my equation here and get the nuclear binding energy. But we're not quite done even after we do that. So let's do that step first. All right, so we get E is equal to 3.4345 times 10 to the negative 5 kilograms per mole times 3.00 times 10 to the 8 meters per second squared. Right, and what we get here is 3.09 times 10 to the 12 joules per mole. And you can see this is a huge value. That's 3 trillion joules per mole. So mole of what, though? This is actually mole of nuclei. So if I had a mole of nuclei, this is how much energy I would get, or I would need to hold it together. Now, this number was technically positive, right? So it's the energy that's being used to hold it together. And that's great. But we weren't actually asked for it in per mole of nuclei. We were asked for it in per nuclei and per nucleon, which we'll get to in a second. So I actually do have to do a conversion here. I know 3.9 times 10 to the 12 joules per mole of nuclei. And I know Avogadro's number. I know 1 mole of nuclei is 6.022 times 10 to the 23 nuclei. Right, so this effectively gets me out of moles and into just per nuclei, like the question asked for. It didn't ask for per mole of nuclei, it asked for it in per nuclei. So this will decrease the number significantly. We now have 5.13 times 10 to the negative 12 joules per nuclei. This makes a lot more sense given that we're only talking about a single atom being held together. It shouldn't probably take that much energy. So let's talk about the last bit here, which is per nucleon. What is a nucleon? A nucleon is a particle in the nucleus, i.e. a proton or a neutron in the nucleus. How many nucleons do you have is dependent on how many protons and neutrons you have in the nucleus. In the case of lithium-6, we have 6 nucleons. So if I want to take my 1.53 times 10 to the negative 12 joules per nucleon, or nuclei, sorry, I know that in one nuclei there are 6 nucleons, i.e. particles in the nucleus, for a lithium-6 atom. This number will change based on the element that we're talking about and how many protons and neutrons are in the nucleus. And this will give me my final answer here for this problem, which is 8.55 times 10 to the negative 13 joules per nucleon. And so these were the two answers that were requested by the problem. You could have been asked to leave it in per mole of nuclei or per mole of nucleons. It just depends on the problem and how it's been written, so you got to be careful with that, whether you need to use Avogadro's number or not. But this is a good example problem of nuclear binding energy. As always, if you have any questions, please feel free to email me or come to a discussion session.